The only genuine historical exhibit in this high voltage room is the one where the spotlight is on now, and perhaps the thing you've come to concentrate on. That is the Marx generator, or impulse generator as expressed in the industry's terms. Now, the circuit diagram for that is on, well, the actual circuit diagram of the equipment is on the bench top, and the simplified circuit diagram is hanging on the wall in the middle where some of you can see it. But basically the elements of any of this style of generator are, first of all, a mains operated step-up transformer and rectifier, which produces some initial value of DC charge. So in this case it's 40 kV. Flat on the floor towards the right hand side of that cluster of equipment is a square grey tank with a brown fibreboard top. That is the transformer and rectifier input for this particular equipment, which was made by the Ferranti company in the mid-1950s. And there's a variac, variable AC input control on this thing, which allows you to go 0 to 40 kV as you so choose as the input. Now the output from that voltage source goes into a ladder of resistors, which you can see for yourself on the left and right hand sides of the vertical stack. And ours is a 6-stage Marx generator with those 6 visible spark gaps at the front. Now, cutting a very long story short, the principle of all of these generators is that you use the input DC voltage to charge any number of capacitors in parallel, and when they are fully charged you discharge them in series, which then multiplies the voltage you put in by n and provides you with a sudden output initiated by the simultaneous triggering of all of the gaps. Now, round on the right-hand end wall, which I think most of you have pressed the button earlier, was a rather cheap homemade model of this thing, which simply had the ladder of charging resistors and the spark gaps, so that when you press the thing, the first spark gap to trigger redistributes the available voltage across the other capacitors and triggers them to go as well, and you just get a slightly uncontrolled simultaneous discharge. In industry, the purpose of this machine was to, with a little cleverer control, to simulate a designed rise time and fall time impulse peak discharge, which simulated if you like, a standard lightning flash. The principle being that when you'd designed your transformer insulation, your cable insulation, your insulator, you would apply, for type approval purposes, a standardized impulse voltage surge to whatever you wanted to test, and it was a pass or fail thing based on the peak voltage applied. So international standards still exist, and I always get this wrong because it's changed, but if you look at the thing in a graph or a oscilloscope representation, right, so the principle is that by adding a second set of resistors, which you can see on the schematic diagram on the bench, not only do you control the discharge time, or discharge rate, which is to do with the resistance and capacitance time constant of the basic capacitors. You've got the so-called wavefront resistors, which determine the initial rise time to a peak. So, Simon, wherever you are, it's 1.2 microseconds up and 50 down, or 60 down? 50 down, yes. I always get confused with the mains frequency on the decay time. Anyway, so with a little bit of clever control and design, you can produce whatever peak voltage you choose of this test waveform. In our own simulation here, we've taken a string of glass disc insulators, such as you see on the National Grid pylons. You can see them hanging from the roof. We've made them faulty, but not completely faulty, by taping short lengths of copper wire across the upper surface of each glass dish. So there's no continuity between the lower one and the earth connection at the top, but it's like a series of spark gaps. And the electrical stress produced by the application of the impulse voltage will simulate actually the failure of those insulators under either a lightning strike or their own test. Now this takes me a moment to get this. Press the white button, please. Under the telephone, there's a white push button. That's it. Well done. Thank you. won't give that guy a job at the power station. Okay, so I'm going to attempt to operate the impulse generator now. It's a little bit fiddly because I've got some remote controls to get on with now. Do we have a red light? Yes, we do. That's encouraging. Now I'm going to raise the voltage slowly from 0 to 40 kV. It may trigger itself, but if it doesn't, I've got a button to press. So it's a very short, sharp discharge up in the ceiling. Approaching maximum voltage now, charging voltage. There it goes. And I can let it do 4 more of those.
Very nice, isn't it? Yeah, so scared. One more. Is that?
Right, I'm going to press the trigger this time. 1, 2, 3. Oh, did it before me. Okay, and I have to turn that off. Right, bear with me while I reduce the voltage. Right, I'm just going to put the... I did one more just as I turned it off. I'm just going to turn the lights on again. Sorry, we've got an automatic timer, so we have to wait 12 seconds to get the light back again. There we go. In the industrial scenario where you've got someone at a remote control desk actually defining when that's going to operate, those of you who can see down to floor level, the bottom spark gap, the right hand end is not connected directly to its associated charging resistor. It's got a small pigtail connection to an insulated thing, which is an ignitron, which is an electrically triggered valve really, or switch, which is under push button control in the normal operation. So although it's easier for us to raise the volts until the thing spontaneously goes over, in actual operation you would stop short of that but trigger the bottom gap to discharge, and then that fires off the rest of it. So that's the principle of your Marx generator. Well, carrying on then, away from static electricity somewhat to some of our other toys. In the right hand window, if I can ask you to move away from me a bit down to the other end, under the spotlight you should... Oh, who's done... Sorry, St. Is that... Yeah. Not with people around, I suggest, but thank you, thank you. In the right hand window you should be able to see under the spotlight there's the upper end of 2 tall copper rods, which are carefully arranged with a wide spacing at the top and a narrow gap at the bottom. Those of us who are familiar with the various generations of Frankenstein film, you'll know exactly what's happening next. This is the so-called Jacob's Ladder, nicknamed, I believe, because a character in the Bible, Jacob, dreamed that he saw angels climbing up a fiery ladder up towards heaven. Well, this demonstration shows you electricity doing that. Now, this demonstration is typically powered from a mains step-up transformer. So it's 50 cycle alternating current. It plugs into the wall and takes in our normal 230 volts, and in this case steps up to 50 kilovolts. Now, in order to stop it actually destroying things, this is high voltage on open circuit, but we've got series resistance, so the short circuit current that we permit from the secondary of this transformer is only 50 milliamps. So 50 kV open, 50 milliamps short, low energy and isn't going to melt the copper. But as I'm sure you're aware, the everyday low voltage relation of this phenomenon is your electric arc welding in the garage. Low voltage for safety, high current to melt the metal. But all of it is electric power arc. Right, this just comes on with a bit of a crack. I'm going to say 1, 2, 3, go, and if you want to see this, you'll need to go perhaps round the corner or right up the other end. Go right round the corner and come back the other side. Has he turned up yet? Right. Anyway, here we go now, 50,000 volts. 1, 2, 3, go! So the travelling upwards effect is just the classic result of air being heated, losing its density and rising. So the high voltage takes the route of shortest distance at the base of the two rods, but the intense heating caused by the arcing effect just causes the hot air to rise, taking the conducting part with it. Up the top, the gap is deliberately set just too wide for that voltage to sustain it, so it blows out. You get another one underneath. There's very little practical use for that kind of device, but a few decades ago, primitive lightning arresters on open wire distribution lines were sometimes fitted with V-shaped arc gaps, which were claimed to put out the power arc that would often be triggered by a lightning surge. But today you have solid-state devices for doing that rather than primitive gaps. Right, ladies and gentlemen, last but not least, but it enables us to tell a little bit of the history about the very famous Victorian age pioneering scientist Nikola Tesla, born in Eastern Europe, but worked first for Mr. Edison's power company in France, I believe, and then ultimately emigrated to the States, where he worked in turn for Edison, who cheated him of money by repute, and then for Mr. Westinghouse, the pioneer of AC power systems. Now, it's thanks to Nikola Tesla's 1888 single-page patent, where he devised, wrote down the diagrams for and patented all the essential components for a multi-phase, alright, we use 3 phases and he started with 2, but a multi-phase AC power system with a suite of multi-phase generators, motors, transformers and so on, sufficient to be the backbone of every national grid or industrial power system that's ever existed since. So as power engineers, we're very grateful to Tesla for really pointing the way as to how to use polyphase systems and transformers. After doing that in the early 1890s, he got very interested in researching in his private lab electricity that was both high voltage and high frequency, large numbers of cycles per second. Please bear in mind that he was playing with this sort of equipment before Lodge and Marconi and other clever people had really shown how we were going to use radio waves at low energy for signalling. That came later. So Tesla, in some ways, was ahead of the game. The device he produced here is an air cord or radio frequency step-up transformer. This particular one is tuned to about 200 kilohertz. I'm not quite sure what frequency Tesla had in mind. But Tesla's dream was that you could do away with most of your distribution network in a locality. No more plugs, sockets, wires, cables, substations or anything. You could build a large tower above your city power station with an enormous one of these generators and broadcast electrical energy right throughout the district. And his scheme was, I think, originally using gas discharge lamps, that the residents in the locality, when they wanted light at night, would simply have to hold their lamp up in the air with a local properly tuned radio receiving aerial attached to it. If the tuning was correct, you would in principle be able to extract enough energy from the transmitted signal to light your lamp. And if you were wearing a necklace or a watch strap or any other thing that happened to tune as well, you'd probably get a bit hot. I mean, it was a wonderful idea and very bold thinking, but commercially, J.P. Morgan lent him some money for his research, but withdrew it, I think, when it became obvious that there was no revenue to be earned from such a thing. Whoever paid to transmit that amount of energy, there was nowhere to put a meter unless the customer was honest, and anyone who provided themselves with the right kind of tuned circuit and light bulb would get free light, so it wasn't going to be any good. And of course, in reality, a few years after this, other scientists and engineers showed us how we were going to use radio for selective, tuned, low-energy communications. If somebody tried to operate a Tesla power transmitter in a town these days, it would just obliterate all our modern communications. So shame, it's never been practical. Well, why am I showing it to you in a museum? Firstly, we had great fun building it, and secondly, it's to this day, though I think they cheat with computers now, the old-style techies in film studios, the sort who would build a Jacob's Ladder for the Frankenstein film, would also build and operate these simply for their gothic horror film, science fiction, theatrical value. And I may have time to mention afterwards there were a number of low-power Tesla coil devices which got used for quack medical purposes. Now, this one has a rotating spark gap, which interrupts a roughly 12 kV supply from a mains transformer fed into a capacitor resistor supply. The diagram is on the window here if you want to see. I'll show it first and then go through the circuit. The spark gaps have eroded in the last few weeks and we haven't had a chance to adjust them, so I've probably got to run it twice before it operates stably. Should be better second time, so I'll have another go. Right, shall I do it one more time if anyone wants any more photos? So, third and last time, here we go. Okay, folks. Now I don't have the right key in my pocket for the next thing. So if you could just stay where you are for a moment, I'll have to go into the control room. So it's a rotating insulating belt on two pulleys, one down the bottom of the machine, another at the top inside the dome.
So funny.
At its simplest, a random static charge that happens to be on one side of the belt, as that goes upwards and the other side of the belt goes down in parallel with it. If like a positive charge going upwards is equivalent to a negative charge going downwards, and if you can extract the charge from one side of the belt with a pointed steel cone as it gets inside the dome, you're actually pumping charge from the bottom to the top. And if, as in this case, you have an extra high tension supply to inject some charge onto the belt at a constant voltage, if the belt is running at a constant speed, the combination of constant voltage, constant speed effectively gives you a current which we've set for this one to, I think it's about, is it 20 microamps or 30? I think it's something like that. Yeah, again this is home built by one of our volunteer team. So the thing is a charge pump. If you just switch it on and press the HT circuit on, well then it will start accumulating charge onto this, in principle, without limit, until something either leaks or flashes over. So for that reason, whenever you operate like these things, the safest thing to do as the operator is to have yourself earthed and always have something at earth potential between it and you. Assuming it's ready to go now, I can just try and demonstrate the length at which its natural output will jump, i.e. the voltage, without any other load. So are we on there? No. We've got a vacuum operated safety switch, so we can stop the charging at any time. So all I'm going to attempt to do is to draw an arc as far as it will originally go. But if I didn't approach with the earth one, it would probably damage itself by flashing over from top to bottom. You don't want to do that. Right, it's not doing as well today as it often does. I think it's the atmosphere. Do we have a drive off? Just polish the water on. Any dust or dirt on the top of the thing, then it leaks away. So I'll put the heater on as well. Okay, thanks. It will normally go down to about there, but I think that's just simply the atmosphere in the room. It won't stop it working as a demo, but in the high summer, when the atmosphere is absolutely dry, you can get a discharge down to about there. We reckon it's about 250,000 volts. Anyway, be that as it may, we'll set it up for a victim. I'll just what we've got, in the early days when we tried this, we got the volunteer to stand holding a tablespoon, actually touching the output of the thing, and on a plastic chair. But the charge transfer rate was so rapid that even with something that wasn't your skin, holding onto the top of the thing, you got a bit of a belt. So we now use a damp broom handle as a, if you like, charge transfer limiting resistor. It's not very scientific, but it works. And the point about the two sticks, we ask the volunteer to stand on the insulating platform and squeeze the two sticks together. That closes the end of this rubber tube and maintains the HT charging supply on. It has two purposes. It is, if you like, it's a safety handle. When one lets go, it stops charging and stops the kids who get up there from moving their hands about. Because the thing you really don't want to do is to be charged up and then point your finger out at something. Well, maybe have the
victim. Your hair might be longer.
No, let me show you.
Oh no, so I believe you. Tom's very consigned his fate.
Well, let's see how it looks then. It's fine.
Well, no, put them on, but tell me if it's unpleasant. They can tingle a bit.
Yes, you just feel a bit of a discharge.
Things like rings and so on and necklaces should be okay. Please just stand up on the green platform.
Should we get some water?
Was this in the health and safety brief?
Now, there's merit there for you to if you'd be so kind as to squeeze the two.
I hope we don't get any explosive discharge.
So, right, yes? Now,
oh, there we go.
What I ask you to do is to shake. That's it. It'll take a while because your hair is quite
Oh, they look so nice.
what we expect. The more you shake and the more you knock your head, the more the individual strands will separate. So the electrostatic effect is just causing. I've got some good work going up in the air. We've actually got a spot there.
You're looking good. Catwalk ready. Oh my god. This is the best thing I've ever seen.
Seriously, not bad.
I know, right?
If you go up and down,
What's the new technique for shit? You can
with always stretch, you're probably diverting the current in a lot of directions.
What do you want to do now? You want to get something earthed and just poke him with it?
keep going, we can do it.
Because he's a charge capacitor.
That's not good.
Not for him, it isn't.
You have enough yet? Keep holding on, we have to discharge you and the machine. Okay. So that's fine, you can let go and there's a step in there.
Oh, here one past.
Thank you, well done. Well done. Anyone from this side want to have a go? No. Together, if you wish to kind. Closer together if you can, that's it. Use both hands, that's it, to hold the rods. And here we go. Shake your head quite hard. That's it, and nod up and down. That's it. It might go a little bit more, but what possibly is
Bad hair day, anyone?
That's what mine looks like in the morning. That's all. Do you want to go up front?
Right, I mean,
pictures, folks?
yeah.
If you're familiar with the right, I don't feel so much. So that's safe for you to let go and come down. Thank you very much. Ever so still, ever so still.
It's worth it.
Absolutely still. And go. Yes. Keep holding on, sir. If it wasn't so damp, they go a lot faster and a lot higher, but that's electrostatic repulsion once again. Stay where you are, sir, just a minute. Thank you, so now it's safe to let go and there's a step to walk you down. The only problem with this is I need to pick all the